All right, today we're going to quickly review caching. Some of you are not familiar with caching per se, and so I want to make sure that you sort of get the general understanding, because we have a lab 2, assignment 2, that talks about you programming your own caching policy, the LRU policy that we're talking about in a moment. Yeah, it would be good to understand what the broader context is of all of this. And after that we'll continue with our review and have a few slides that I will present that I inserted in the slides for Monday, so you can find them there now. But I did not talk about those because given the comments after the Monday lecture, I figured out that that would be very helpful to add. So let's talk about caching. So first, if we're thinking about our memory layout, we notice that all the computation happens at the CPU, right? So that means that everything that you can find in its own registers is easily accessible, meaning that also like the closest cache is easily accessible, and so if the right information is already present in that cache over there, then you will introduce very little speed overhead, if you will. So you don't have to wait for too long to get the information that you need for your computation. So that's what this hierarchy essentially demonstrates. You have a bunch of storage. This is all on core. It's close to the CPU, and you have say different levels for your cache, say level 1 and level 2. This would be called the lowest level cache. And now you may not have enough space here, because apparently if you're so close, then you cannot store too much. It would also be too expensive. So that means that you need to sometimes evict information from your cache to, for example, DRAM over here, right? So DRAM has a physical address layout, but we use it as virtual memory often, right? With address translation that we've talked about before. But even DRAM can run out of storage, and this is all temporary, by the way. Then if you want to make some more space, you need to actually do some page swapping from DRAM out to other storage devices. In STX we talked about having in DRAM an EPC an EPC range, right? And that range also needs to have pages that may need to be swapped out to other parts in the DRAM. So we have been talking about two different kinds. So here we talk now about two different kinds of page swapping. One is the page swapping from trusted DRAM in the where the secure enclaves are stored, and it's a limited amount of space, to untrusted DRAM, and then on top of that you can have page swapping out into, say, disk. And then of course you have other types of, if you will, storage devices which are all about input to your computation, to your PC, for example. So this is the hierarchy. So in order to increase speed, you need to have a good methodology for what you want to keep in cache and what you would like to evict out of cache, because once you evict it out of cache, and if you need it again, you will really incur a performance penalty. So effectively we talk here about a memory hierarchy, and let me talk about all of this together. So effectively it provides memories of various speed and size at different points in the system, and we use a memory management scheme which will move data between the levels, and those items that are most often used, you would like them to be stored at the faster levels and others at the lower levels. So the cache is just a small fast buffer that lies between the CPU and the DRAM essentially, and it holds the most recently accessed data. That's what you would like to have, because that is a good predictor for the future, and you assume that you will reuse that data actually all the time and update it all the time. Virtual memory is something different from cache. Here, program and data are assigned addresses independent of the amount of physical main memory storage, and effectively we have this address translation that we talked about in a lot of detail in one of our first lectures. It's very important when we talk about the cache to think about the hit ratio, which is the probability that the next memory access is found in the cache. If that happens, then you're good, so you do not have much of a performance overhead. So you would like to make this as large as possible, so the miss rate as small as possible. And you can do some simple exercises if you want to see what the effect is of a larger and lower miss rate. And you really see a dramatic performance increase in general if your miss rate is going to be smaller. You see that it's 3 orders of magnitude. So the primary goal of the cache is to increase speed. The primary goal of virtual memory is to increase space. So what are we going to talk about with respect to cache design? We're going to talk about placement, so where can a block of memory go? Identification, how do I find a block of memory? And replacement, how do I make space for new blocks? Then you have a write policy, so how do I actually update? And then we consider these for caches, but clearly you can also apply these kinds of principles to other memory boundaries. So if we talk about placement and identification, so we're talking here about the cache, right? Then we're going to talk about these 3 kinds. And we talked about it before, but I will repeat it so that we have a good understanding of how it works. So first, effectively in a full associative mapping, a memory block can map into any block in cache. And here we see this example where we have the main memory, so a bunch of possible addresses with data and so on. And the cache is limited in space. And what we do is we can simply, anywhere in the cache, we can store, say, a block. Say, for example, I'm storing in the first block of the cache, I store data A, which is this one that has this address. So I need to store both the address that corresponds to this particular memory item, and I store it all in my cache. So that's one way to do it. Now, if you do this, you would actually have a more complex decoding circuitry. What you need to do is you need to consider everything that's in the cache, and you need to simply check whether the address that you're interested in is actually there. So the tag that we talk about here has that address that we are going to verify, and then we will figure out the data. And in general, if we have an address, we split it up in that tag and an offset, and the offset will then figure out within this particular cache line what part we are interested in. So that is usually how we are thinking about it. Advantages, no contention. I mean, if there is space in the cache, you can keep on storing stuff in there. It's easy to implement, but it is very expensive. It's a lot of circuitry and very wasteful of cache storage. Very wasteful, but yes, you need to also store the full primary memory address. So that would not be a good thing to do, maybe, because it's just an extra amount of memory that you need to do, but generally it's not that much, so I don't know whether it's such a bottleneck, to be honest. Direct mapping. So what we now do is we store the higher order tag bits along with the data in the cache. So we effectively have a split in index bits as well as tag bits. So now what we do is we effectively have 4 possible blocks, but they are colored, if you will. So this one is called 00, 01, 10, and 11. And unfortunately, only those that have as address 00, like this one or that one, can be stored in block 1. This particular program A item that corresponds to this address cannot be stored over here because 01 is not equal to 00. So program A can only be stored in block 1, and also data A can be stored in block 1, so that can lead to contention. So if I'm interested in having both of these items to in my computation, so some variable here and some other data here, then I need to evict one for the other all the time, and that is expensive. So that's how direct the direct mapping works. Yeah.
If we need data A, then we'll have to evict program A, right?
I'm sorry?
So if we need to put data A in cache, then we'll have to remove program A.
Exactly. That's so that's exactly what I hoped to explain. That this block A in block in block 1. Program A can only be stored in block 1, and data A can only be stored in block 1. So what does that mean? If it's already occupied by program A and I need data A, I need to evict program A and I get data A. Then after that I need program A again, I need to evict data A and bring program A in. Now, that's a problem if I'm interested in both a lot. Then I need to evict all the time and bring it back from main memory into the cache. And that's expensive in terms of computation time. So that's what we just explained. That's the contention with main memory data with the same index bits. Now, it's low cost. Look at this particular decoding circuitry, because I take the address, I immediately figure out which, cache line I'm interested in. And then I'll just have to figure out what the offset is and whether it fits. And if so, if that tag fits, then I just bring it out and I have a cache hit. Otherwise, would have a cache miss. So it uses less cache space. That's also true. But again, I'm not so sure how much that matters nowadays. But yeah, you save in this case 2 bits. Now, a good in-the-middle solution that tries to bring both solutions together is a set associative mapping. Now, this is a slightly different methodology, but it tries to inherit both. So the idea is that we now work with sets. So what does that mean? The idea is that I still have tag bits and index bits. And the tag bits over here, they indicate where I can store program A in this particular case, in what set I can store it. Okay, so program A I can store in set 1, but I noticed that there are 2 possible spots for storing program A. So that's more flexibility than the direct mapping, where I only had 1 spot to store a value. So clearly, if I now have program A and data A that I'm interested in at the same time, and they're both actually indexed by the 0 over here, then I can store both of them. But notice there are more zeros, like all the other ones. So also, besides program A and data A, also program C and data C are all mapped to set 1. So I still have contention, of course, but there's a little bit more flexibility, because if I would not be interested so much in program C and data C, then I'm pretty happy, because this is what I use during my computation all the time, and I have space and it's right there. So I make it a little bit more flexible. I'm in the middle. I don't have a direct mapping to a single location in my cache memory. It's also not that I have a full associative mapping, right, in which I can literally store this everywhere. No, I'm saying I can store this in a subset of my cache memory, as said, and hopefully there's enough space that I limit the amount of contention that I will see. Now you save a little bit of memory now, because I still need to store an offset, the tag bits 0, 0 and 1, 0, because program A is identified by 0, that's the set's color, if you will, right? But I also need to identify that I'm actually talking about this address, so I need to store the 0, 0 here as well. Okay, so it's a somewhat in the middle solution, and here you would think of having the sets sort of depicted across here. So we split the whole cache in say we have sets of 2 variables in this particular case, 2 locations. Then I split the whole cache into 2 parts. The address is now split up and it produces an index. So I'm looking at a specific set. Now I need to figure out which location in that set I'm actually interested in. So I'm going to use my tag to find out whether it's in there in the first place, and if it is, then I get it, and I have still an offset that will sort of within that block will tell me, you know, what I'm interested in. So we can have a one way would be the direct mapping, sets of size 1, 2 way would be sets of size 2, that was the previous slide. 4 way and 8 way are larger set sizes, and you see that you have a little bit of an improvement, and so most structures have maybe a 4-way structure, and that's also what Intel SGX I think is doing. Pretty convinced they have that. So also in your assignment you are working with a 4-way set associative cache.
What does this mean, the parameter delta?
The difference between those two. Yeah. So you see how it improves a little bit. At some point it converges, right? It stabilizes. So why would you even go more than 4-way? It's maybe not too much of an improvement anymore. So there are all kinds of replacement policies. So now we have just talked about essentially identification and what was the other thing? And placement. But what about replacement? So suppose I need to make space because there's contention. I need to bring in an element from memory, but there's no space in that set. So what do? I need to, unfortunately, I have to evict one of those members of the set in order to generate space for the new element, for that new piece of memory. So how do we choose that victim? Well, there are many policies. We're not going to talk about any of them except for the LRU, the least recently used, because that's the one that you actually use in your Lab 2 assignment. It also turns out that this is a really good strategy, maybe a little bit more expensive, so that's why you may want to think about a sort of a pseudo LRU that you want to implement. But anyway, let's have a look what that means. So it's the least recently used strategy, and here A indicates the set size, and when A equals to 2, then the LRU is what is equivalent to what we call not most recently used, and that simply is a very simple strategy where you have just one pointer to what is the most recently used element in his set, and if you need to evict something, you evict something that lies outside of that's one of the other entries, and you choose that at random. Now for A equals 2, that would be the exact same thing. For A larger than 2, it's slightly different. Then we have a really different strategy. LRU may become difficult, expensive. Do we need timestamps? Because you need to know the order of all these entries in your cache, like from what is the most recently used to least recently used. So you may even want to have a priority queue. That's not how people implement this, I think. But you can have timestamps if you only have a set size of 4, which you do in your lab. Then, by the way, you are building a simulator. So who cares really how you figure out what is least recently used in an optimal hardware perspective? In a simulator, you can actually simply use, implement whatever you want. You can use timestamps, you can use a priority queue or whatever you want. You could do that. But the point is that in hardware, you need to be a bit more careful. And so, yeah, if you have a sorted list, do you do that? Then you need to resort it on every access and so forth, and the list overhead will be kind of painful. You have more circuitry around it to make that happen. Do you really want to do this? So you can have an LRU counter for each line in a set, and when a line is accessed, is being accessed, then you want to get the old value of its counter. That's one approach. Set its counter to the max value that you originally started with, and for every other line in the set, if the counter is larger than X, you are going to decrement it. That's a very fast way of sorting, and when replacement is needed, you select the line whose counter is 0, and it turns out that this is actually working well. You can think about it, you can build in the right algorithmic invariance to show that you always have one counter at 0 if you do this in a proper way, and you will also be able to always have a nice clean ordering of everything. It's a very nice implementation.
Can you demonstrate the previous slide algorithm?
Which one?
Yeah, this one.
What algorithm?
Set clear on each access. How we can show the list recently used only with one bit?
Well, if you have timestamps, well, the next slide actually explains one version of how you could do that, which implements a sorted, effectively timestamps or counters that sort all the entries
So we need more than one bit.
in the set. The list overhead is log 2a bits per block. No, that's good enough, right? That's the number of bits you need extra per block to store as a counter value. And if you have a list itself, if you think about the access time, and say you have a sort of you have some list structure with pointers and maybe a linked list type of structure. So if you look at data structures, then that's probably the way to do it. Then you can, with some variability maybe, well, anyway, whatever. But then you would be able to jump through very fast in logarithmic amount of time, actually, and fit and find the right spot. But the next slide actually shows you a very nice, efficient implementation.
So you were asking that if A equals to 2, then why do we need 1 bit?
How we can
Because A is actually the number of sets. So if you have 2 sets, so you can just set 0 to one set and 1 to the second.
The size of the set. No. A equals 2 is the size of a set. So you can have many sets, but you have the number of ways is this. Yeah, so it's the number of blocks, cache lines that you can store in a set. So if it's only 2, then one is the least recently used and the other one is the most recently used. Yeah, in each set, yeah. So that's all symmetric, right? So each set has a certain number of elements in it. The set size is equal for all the sets. And here, in this example, the set size is equal to 2, here larger than 2, and here, and that's it. Yeah. So the next slide, though, explains an algorithm of how you could figure out what is the least recently used. So that's maybe the answer to your question, actually, is this slide. So what do? You have some ordering. So say you have 8 elements, 8 ways, or the set size is 8, so 8 cache lines. You can have multiple blocks in a cache line, so that's why you had the offset to select one of the blocks in there, but that we don't talk about here. Anyway, you have 8 cache lines. So those 8 cache lines, they each have a number, ranging, say, from 0 to 7. So 3 bits each. So now what I do is, I'm going to take one element that I'm interested in, say, which was indexed by 5. Then everything that was indexed by larger than 5 will be decremented by 1. So the 6 goes to 5, the 7 gets 6, and the 8 gets 7, and the one that I just was accessing will get the maximum counter value, which is 8. So again, everything is ordered, and the most and the least recently used is being put on top. That means that the 0 indicates the one that is the oldest and not the least recently used, sorry. And that means that one I can evict. So the most recently used has the counter 8, right? Up to the least recently used is counter 0. So you can just play with this, and that will be a very simple algorithm to make that happen. But you still need to implement it in hardware. Now there are other kinds of things, so I just want to show you that people do tons of research in this area actually, or at least in the past. I don't know how active it is still. But you have like a more practical pseudo-LRU, where you essentially have a different kinds of sorting mechanisms. You use a binary tree, where going, say, to the top and to the bottom here indicates older or newer. So you don't have a complete ordering in a sense. But in this way you can have fast updates, and you do have and you do not necessarily get the least recently used, but you can follow the older points. Oh no, you do find the least recently used victim, but yeah. So this is an interesting way to do it. So what are the LRU shortcomings? Okay, so apparently, and I don't know the details about all of this, to be honest, but you can have certain patterns that this LRU mechanism actually leads actually to bad performance. So sort of a worst case access patterns, and that you need to be careful about. So here we talk about the reuse distance, which is the distance to the next reference of a block. And so what you, in an optimal sense, would like to have is you would like to know the future, to know what you should have in your cache. So that's why we're interested in the reuse distance, so that will tell you something about how likely it is that you will have a miss or not. So anyway, so there are apparently some problems that we need to consider. And it seems that making a less precise LRU may sort of mitigate that somewhat. All right, so there are many other, so what in your assignment? So in your assignment you have 64-byte cache lines, which is standard, and the set size is 4, and you will use LRU. So in the simulator, as I said, you can simply use actual timestamps. I mean, what do you care? But in practice, you do it in a really efficient way. So that's what we just discussed. So what about your write policy?